So now that we know all of our different trig derivatives, let's go ahead and take a look here at example number 3 and 4 to try to see just how we can use these in some different questions. So we'll start here with example 3, which is going to highlight a very, very important idea for us. Suppose that the position of an object on a vertical spring at time t is given by f of t equals 4 cosine t. Okay, so I'm just imagining that I have an object and I can tell its position by plugging t's into this formula. Well, I'm being asked now to find the velocity of the object at a time t. So I want to find like a velocity formula for the object as opposed to just where the object is. To get kind of a visual, let's suppose that maybe like this is my spring, right? And here's my object that's maybe at the bottom, right? And so this object is going to obviously be, going up and going down and constantly maybe ping-ponging back and forth. And so maybe a cosine function models that pretty well because we know that cosines kind of create like a wave sort of a function. So if this is the case, then how do I start to, understand how I find this velocity? Well, again, if f is just telling me where this object is located, then finding the velocity is trying to understand how quickly that position changes. We actually talked briefly about this back at the start of chapter 3 when we looked at a problem that involved a truck that was moving, and we were interested in reading its speedometer at different points in time. So we have this kind of interesting relationship that is going to be formed. If I ever know the position of an object by taking its derivative, which I'm going to imagine as kind of going down a level, so to speak, I can obtain the velocity. That is, I can understand how quickly a position is changing by measuring velocity. So notice like maybe position is measured in meters, but velocity then can be measured in meters per second. If I was to go down another level, I could actually then figure out how quickly velocity is changing. And that would be by measuring something like acceleration. If I want to know how quickly the speed of my car is changing, whether it's going up or going down, that's accelerating, right? So that's like how hard am I stepping on the gas or on the brake to speed my car up or slow my car down. So there's an interesting derivative relationship between these three important concepts: position, velocity, and acceleration. If I start with position and take the derivative, I can get to velocity. If I take the derivative again, I can get to acceleration. I can also take the derivative of acceleration. Anybody know what the derivative of acceleration is called? It's actually kind of funny. The derivative of acceleration is what's called a jerk. So it's also a great way to just mathematically insult somebody. You can call them a derivative of acceleration. You've said that they're a jerk. Classic. If you want to take the derivative of a jerk, you actually get what's called a snap. And if you take the derivative of a snap, you get a crackle. And if you take the derivative of a crackle, you get a pop. So it's acceleration, jerk, and then snap, crackle, pop. That's actually true. You could go ask or look up stuff related to physics, and that's actually how they're labeled. It's kind of humorous. So for this example, since we're already told the position function, and we want the acceleration, we want the velocity, we just need to compute f prime of t. And that's actually super easy, because I recognize that I can use constant multiple rule here at the start and just leave the 4 alone, and then I can just multiply on by the derivative of the cosine. And the derivative of the cosine is negative sine. So overall, I'm going to get negative 4 sine t is going to be a formula that models the velocity of my object. And so I could even relabel it as v of t, indicating that it measures a velocity. Now let's take a look here briefly at the very last question here, which is example number 4. And this is going to bring up some ideas that we talked about back in the product rule. Here we're just being told to just differentiate this function. But we'll notice again that this has 1, 2, 3 different functions in it. And so we're going to have to use this kind of three-way product rule that we discussed back in the product rule section. So remember how that worked. I just had to start by taking the derivative of one of these items and then leave all the other items alone. So I'll start by taking the derivative of the x squared. That'll be 2x. And I'll leave the other two items completely alone. Now I can go ahead and maybe say, this time I'll take the derivative of the sine function. And that, of course, will get me cosine. I can then go ahead and leave the first two pieces alone and take the derivative of the cosine function. Notice that gets me negative sine, and I'm going to write that in an extra set of parentheses so it doesn't look like I'm subtracting sine. I want to make sure I'm very careful that if I'm multiplying something on, I put like parentheses around it, especially if it's got like a minus in front. Well, now notice that if I wanted to, I could like simplify this up a little bit, right? I have 2x sine x cosine x. Over here, I have an x squared cosine squared. Over here at the back, I technically have a minus x squared sine squared. So there are some things that I could do to actually simplify this down a little bit and use some different trig identities to maybe make this look a little bit neater. In the notes up online in Blackboard, I actually show some of those simplifications, so I won't bother doing that here. If you're interested in how you might be able to simplify with some other trig identities, go take a look at those notes up there. And of course, please by all means, feel free to ask me any questions. I know that there are a lot of derivative rules that we've talked about thus far, and if you've been taking a look at this derivative rule sheet, you'll see that there are a lot more derivative rules still to come. So don't be too overwhelmed by looking at the whole sheet all at once, but try to focus on understanding and remembering the rules that we actually have talked about thus far. And the best way to do that, as always, is to go to the worksheets and to practice using these derivative rules. That way you can start to dedicate them to memory. If you have any questions or need help with any of this content, by all means, please let me know.